Hello viewers, in today's session we are going to discuss some important problems from limits involving inverse trigonometric functions. And before solving the problems involving limits in which inverse trigonometric functions are involved, let us first quickly see two important results related to limits involving inverse trigonometric functions. So here we have the two important results. The first one is a limit x tends to 0, and here we have a sine inverse x divided by x is equal to 1. And the second result is a limit x tends to 0 and tan inverse x over x is equal to 1. So these are the two important limits which are usually used while evaluating limits involving inverse trigonometric functions, right? So these are the two important limits. So here let us first quickly see the proofs of these two results. So now to prove the result 1, let us first make this substitution, that is sine inverse x is equal to theta, right? So we have x is equal to sine theta, and here x tends to 0. So when x tends to 0, then sine theta tends to 0, which implies that theta tends to 0, right? So now this limit, that is a limit x tends to 0 sine inverse x over x, now takes the form limit. So x tends to 0 implies theta tends to 0, and for sine inverse x we have theta, and for x we have sine theta, right? So we have now limit theta tends to 0, and here we can write theta over sine theta as sine theta over theta. So now we have limit theta tends to 0 sine theta over theta, and here we have the numerator 1, right? So now this is the standard results in limits, and the value of limit theta tends to 0 sine theta over theta is 1. So we have 1 over 1, that is equal to 1. So the value of this limit is equal to 1. So what we have done here, we have made this substitution, sine inverse x is equal to theta. When x tends to 0, then sine theta tends to 0, which implies that theta tends to 0. So here we have used this result, limit theta tends to 0 sine theta over theta is equal to 1. So let us now prove the second result. So now to prove this result, we'll follow the same steps which we have followed while proving the result 1. So here we'll make this substitution, that is tan inverse x is equal to say theta, so that x is equal to tan theta, and when x tends to 0, then tan theta tends to 0, which implies theta tends to 0. So now this limit, that is limit x tends to 0, tan inverse x over x, it takes the form in terms of theta. So here we have now theta tending to 0, and for tan inverse x we can now write theta, and for x we have tan theta. So now we can write here 1 divided by limit theta tends to 0, and here we can take this theta to the denominator of tan theta. So we have tan theta over theta. So we have 1 over 1, because this is the standard result in limits, that is limit theta tends to 0, tan theta over theta is equal to 1. So we have here 1 over 1, that is equal to 1, right? So these two results play an important role while evaluating limits involving inverse trigonometric functions. So now let us solve some problems. So here we have the first problem, limit x tends to 0, tan inverse 2x divided by sine inverse 5x, right? So here we'll make use of these two results. So let us take the value of this limit as L. So we can now write L is equal to a limit x tends to 0. So now see here, the numerator is tan inverse 2x and the denominator is sine inverse 5x. So let us convert the numerator and the denominator into these two forms. So let us write here tan inverse 2x, and here we divide tan inverse 2x by 2x, so that here we have this form, that is tan inverse x over x, and then here we multiply this term by 2x, so that 2x and 2x get cancelled, right? And in the denominator we have sine inverse 5x. So let us write the denominator of sine inverse 5x as 5x, and let us multiply this term by 5x, right? So now we have here a tan inverse 2x over 2x, which is of this form, and sine inverse 5x over 5x, which is of this form. And here we have the two factors, 2x and 5x. So let us cancel these two x, and we have here a 2 over 5. So we can now write 2 over 5 in front of the limit notation, and we can now write here a limit x tends to 0 tan inverse 2x over 2x divided by limit x tends to 0 and sine inverse 5x over 5x, right? So now here we have a limit x tends to 0, and here we have a 2x, right? So when x tends to 0, then 2x also tends to 0. So here we can now write limit 2x tends to 0. And similarly here we have 5x. So when x tends to 0, we can now write 5x tending to 0. So here we write limit 5x tends to 0. So now this limit is of this form. So the value of this limit is now equal to 1, and the value of this limit, which is of this form, is also equal to 1. So we have here simply 2 over 5. So the value of this limit is equal to 2 over 5. So now let us solve this problem. Here we have limit x tends to half, and we have x minus cos sine inverse x and 1 minus tan sine inverse x. So here to evaluate this limit, let us first make this substitution, that is sine inverse x is equal to theta, right? So here we have sine inverse x, here also we have sine inverse x, so that x is equal to sine theta. Now here x tends to half, right? So when x tends to half, then sine theta tends to half, and it implies that theta must tend to pi over 6, because sine pi by 6 is equal to sine 30 degrees, that is half, right? So let us now transform this limit in terms of theta. So here let us take the value of this limit as L. So we have now limit, and here we have theta tending to pi over 6, and let us substitute here for x. We can now write sine theta, and then we have cos theta. For sine inverse x we have theta, and here we have 1 minus tan theta, right? So now this is a trigonometric expression, right? So the purpose of making this substitution is to convert this limit into the normal trigonometric functions, and then we can make use of the standard identities in trigonometry, right? So let us solve this expression. So we have limit theta tends to pi over 6, and here we have sine theta minus cos theta, and here 1 minus sine theta over cos theta. So we can write for tan theta sine theta over cosine theta. So now we have limit theta tends to pi by 6. Let us solve it. So we have sine theta minus cos theta, and here we have cos theta minus sine theta divided by cosine theta, and we can take cosine theta to the numerator, right? So here we see that we have sine theta minus cos theta, and here we have cos theta minus sine theta, right? So let us take the negative sign common in the denominator. We have limit theta tends to pi by 6. We have sine theta minus cos theta, and here we have minus sine theta minus cos theta, and here we have cosine theta. So now these two terms are same, so these two terms get cancelled, and we have here the negative sign. Limit theta tends to pi by 6, and here we have cosine theta. Now limit theta tends to pi by 6, cosine theta is simply minus cos pi over 6. Now this is cos 30 degrees. The value of cos 30 degrees is square root of 3 over 2, right? So the value of this limit is minus square root of 3 divided by 2. So now let us solve this limit. So here we have limit x tends to 0, 1 over x, secant inverse 1 plus x square over 1 minus x square. So here we can again make use of the method of substitution. So here the appropriate substitution is x is equal to tan theta, right? Because here we are going to make use of this identity, that is a cosine 2 theta is given by 1 minus tan square theta divided by 1 plus tan square theta. So here making this substitution, we have now x tending to 0. So when x tends to 0, tan theta tends to 0, and this implies that theta tending to 0. So now let us take the value of this limit as L. So we have L is equal to limit theta tends to 0, and here we have 1 over x, so we can now write 1 over tan theta, and here we have a secant inverse and 1 plus tan square theta divided by 1 minus tan square theta. So now here we have cosine 2 theta is equal to 1 minus tan square theta over 1 plus tan square theta. So let us take the reciprocal. So here we have 1. So 1 over cos 2 theta is given by 1 plus tan square theta divided by 1 minus tan square theta. So inverting this fraction here, we have now a limit theta tends to 0, 1 over tan theta, and here we have secant inverse, and this expression is now equal to 1 over cosine 2 theta. So now 1 over cosine 2 theta is equal to secant 2 theta. So now we have limit theta tends to 0, 1 over tan theta, and here we have secant inverse secant 2 theta. So now we can write limit theta tends to 0, 1 over tan theta, and here secant inverse secant 2 theta is simply 2 theta by using the properties of inverse trigonometric functions, right? So secant inverse and secant x is equal to x, right? So here we can now write this expression as 2 times limit theta tends to 0 theta over tan theta. So we have now 2 times 1 over limit theta tends to 0, and we can now take this theta to the denominator of tan theta. So we have tan theta over theta. So now using this result, we have 2 times 1 over 1. So the value of this limit is equal to 1. So this is simply 2, right? So the value of this limit is equal to 2. So now let us consider another problem. So here we have to evaluate limit x tends to 1 minus the negative sign shows that we have to find out the left hand limit of this function when x approaches to 1. And here we have 1 minus x divided by the square of cos inverse x, right? So here to evaluate this limit, let us first make this substitution, that is x is equal to 1 minus h, where h is a positive quantity and it is infinitesimally very small, right? So here since we have to find out the left hand limit of this function when x approaches to 1, therefore we take this substitution x is equal to 1 minus h, where h is infinitesimally very small and it is a positive quantity, right? So when x tends to 1, then h tends to 0. So now this limit can take the form limit h tends to 0, and here we have 1 minus x, x is 1 minus h, and here we have cos inverse of 1 minus h, and here we have the square, right? So now we can write limit h tends to 0, and here we have 1 minus 1 is 0, and here we have simply h, and we have cos inverse 1 minus h and square, right? So let us now make another substitution here, and let us take cos inverse 1 minus h as theta, so that we have cosine theta is equal to 1 minus h, right? So the value of h can be written as 1 minus cosine theta. Now see, here h tends to 0. So when h tends to 0, then cosine theta, which is equal to 1 minus h, it tends to 1 minus 0, that is 1, right? So cosine theta tends to 1, so this implies theta tends to 0, because cosine 0 is equal to 1. So now we can express this limit in terms of theta. So we have now limit, and for h tends to 0 we have theta tends to 0, and for h we can now write 1 minus cosine theta, and here we have cos inverse 1 minus h, that is simply here we have theta square, right? Because cos inverse 1 minus h is equal to theta. So now we have to evaluate this limit. Now in order to evaluate this limit, we'll make use of an important identity from trigonometry, that is 1 minus cosine theta is equal to 2 times sine square theta over 2. So now this limit is equal to limit theta tends to 0, and we have 2 sine square theta over 2 divided by theta square. So now let us try to express this limit in this form. So we'll write here a limit theta tends to 0, and here we can now write 2 sine square theta over 2, and here we can write theta square over 4, and here we divide theta square by 4 and multiply theta square by 4. So now we have this term, right? So here we can now have 2 times 2 is 4, so we have here half, and limit theta tends to 0, and we can now write here sine theta over 2 divided by theta over 2 whole square, right? Because here sine square theta over 2 and here theta square by 4 can be written as theta by 2 square, right? So now this limit is in this form, so we have now half and we have limit, and when theta tends to 0, then theta over 2 also tends to 0. So we have here theta by 2 tends to 0, and sine theta over 2 divided by theta over 2 whole square, and this limit is equal to 1 due to this result. So we have half times 1 square, that is equal to half times 1, that is half. So the value of this limit is equal to half.